So it carries 40%. And the final examination will carry 60%. Okay. And what you need is you have two tests here. You have test 1 and test 2. So this will be carried on week 6. This will be carried out on week 12. Okay. This is from this is what is planned. In this is the initial plan. So final exam for now, for the coming final examination is face to face. It's physical. So you need to come back. It is no longer online anymore. So you need to come back to the campus and sit for the examination. Okay. Physical examination. Okay. Then how many questions? How many questions are there? Normally is 5 questions. 5 questions. Okay. Cover most of the topic that we will go through for this course. Cover all the topics in this course. So for this course, essentially we are just dealing with static fields. So like in mechanics, if you, let's say you have go through some physics courses before. So when we study mechanics, there are statics and dynamics. So same goes for electromagnetic fields. So we have static fields and dynamic fields. But we won't touch dynamics. We only touch static fields. So in the static fields, we have electrostatic and magnetostatic. And when we mention static fields, that means since you are from electrical and electronics engineering background, so I suppose that you should know what is charge. Yeah. So when the charge is moving, okay, at one direction at a constant speed, so then we have a current. So we have when the charge is moving, then we have a current. So when we deal with electrostatic, then we have charges in stationary, they are not moving. And when we are dealing with magnetostatic, then the charges start to move in a steady state, in a steady state form, and they move in one direction, and that produces magnetostatic. So we will deal with that a little bit more when the times arrive. So we have 5 questions altogether. 5 questions, cover all topics. Basically, we cover the learning outcomes. So I believe you know what is the learning outcomes. Just let me just bring up the what is the learning outcomes. So as I mentioned just now, we have electrostatic and magnetostatic law. So you must be able to classify what is the electrostatic and magnetostatic law. So given a questions to you, so you should be able to identify which law to use that for a particular problem. So apply all the postulates to solve electrostatic fields and magnetostatic fields. And you should be able to characterize electric field and magnetic field for given geometry and boundary conditions. So we will learn all this in the 9 chapters that we will go through. Okay. So for this topic here, I mean, the mathematical fundamentals for EMF, I put chapter 0. So this chapter here is supposed not to be assessed. It shouldn't be assessed for, in this course. It is basically the mathematics that you need for this course. So that's why I put chapter 0. So as I said, I will go through with you some of the maths that you need. I do some brief revision for this tutorial session, and then when the next hour, during the lecture hour, then we will solve some real problems coming up from the for the electromagnetic fields. Okay, so let's start with vector first. So for this course, you need vectors, and you need to know a bit of calculus, solving integral equations. Sorry, not integral equations. Solving integration problems. Simple integrations problems, but of course we are dealing with 3 dimensions, because we have we are dealing with three-dimensional space, so we need to know vectors, and as well as solving the problems, the calculus problems that arises from these topics. Okay, let's move on. So let's start now. So I think that's enough information for you. Okay, before I move on, just one quick check with you. Any questions that you want to clarify before I start? Yes, Muhammad Adin. It's going to be tough if you don't do if you don't do the work. If you don't try to understand it, and if you leave it until the end, and then you try to cope, then it's going to be hard, definitely. So when I say you should try to do your tutorials, try to attempt the tutorials, and then if you cannot attempt, then ask me during tutorial sessions, or you can email me, or you can ask me during lecture sessions. Then I will provide a solution to you. Kok Wing, we have no, we do not have assignment or lab, only tests. So the test is your coursework. So this course is going to be hard. As I said, it is only going to be hard if you try to sit on it. You try not. If you're not trying to be, understand it. So by understanding it, you just have to solve problems like mathematics. So an honest answer from me, a very honest answer from me. So I will, for the first time, for the first week, I will go through slowly. I will try to explain the steps to you. So try to, as I said, if you don't understand, just let me know. I try my best to explain to you again. Otherwise, we have to, set an appointment, a consultation appointment, and go through uh, a private, a private one-to-one sessions. So if as I said, if you need all this, just let me know. So you can always email me if you want to have a consultation hour. Just let me know. Okay. Any other things that come across your mind that you want to ask? Okay, if you do not have now, so we will start with some revision on the maths. Okay, so we will start with vector, scalar, and vectors. Scalar means you have a quantity that there's a measurement on magnitude. Scalars is there's a quantity only magnitude and no direction. Vector, they have both quantity and magnitude. So for example, scalar is like scalar quantity like temperature, mass, pressure. So they do not have any direction or speed. I'm not talking about velocity, I'm talking about speed. So if speed, then they do not have directions. So directions like quantity, example like vectors. So we have velocity, we have force, we have displacement, electric field. So these are the example of vector quantity. Okay, so EM theory, electromagnetics theory, is the study of some particular fields. So in the particular fields that we are referring to is the electric field and magnetic field. So when we talk about fields, we are talking about a quantity at a point. So my keyword here is at a point in space. So that means, for example, if let's say we talk about temperature in a room, right? So it is not necessarily constant throughout a given space in a room. So at any point in, let's say, a three-dimensional room, for example, the room that you are sitting in now, so we have different temperature at different point. So in other words, the temperature function in your room is a three-dimensional functions. So XYZ, for example. So fields describe, so you must have a function that describe a quantity at a point. Okay. So unit vector. So a unit vector is the vector itself. So for example, I have a vector A in this case, and the unit vector is a small cap A, and the whole vector here is capital A, and small letter a is the unit vector. So if I want to represent vector A is the unit vector multiply the magnitude of this vector here. So this vector here there has a magnitude of A pointing in a unit vector direction A, small a. So a unit vector means that you have a magnitude of a unit, 1. That's why it's called unit vector. So in Cartesian, is always, if let's say I have a point in a 3-dimension, okay. So as you can see here, the x, y, z, x cap. So we call this a cap. So x cap y cap and z cap direction. So these are the unit vector direction in the direction of x, y, and z. So I can represent a vector A, this point here, if you can see on my screen, I'm trying to put some color at this point. So A, this vector A is represented by x cap, y cap, and z cap. So, and its associate magnitude AX, AY, and AZ. And you should know the magnitude of this vector here, the magnitude of A now, can be found as the x component square, the y component square, plus the z component square, and then the whole thing square root. So, yeah. So these are all fundamentals that you should know. So vector algebra. So additional vector, and so how we add. In this case, that's for example, I have vector A, B, and C. C is the resultant. So vector C is the resultant of adding vector A and B. So as you can see here, this vector B in this direction, vector A is in this direction. So the head is pointing to the tail of A. So this is vector A. So as the head of the vector B, which represent the end of the end of the vector, pointing to the beginning of vector A. So that this form a triangle. Okay, this form a triangle, and we say that A plus B or B plus A is equals to C. So this is the vector addition. And we have also subtraction. We also have subtraction. So if vector B pointing in a different direction, then it's A minus B. If two vectors are equal, means that the direction and the two vectors is equals when the magnitude and the direction of two vectors is the same. For vector multiplication, we have a few of them. One is a simple product between a scalar and a vector. So the resultant of it, when a scalar multiply a vector, it will be a vector. Then we have a dot product, and this one is important, and I will show you why later on. When two vectors are vector dot product, so vector multiply a vector, this dot product, we have a formula here. A dot B is equals to AB cos theta. So the product of it, the product of two vectors, dot product, is a scalar. While cross product, two vector cross each other, it produces a vector. So all these are vector multiplication. We do not have vector division, so we cannot have a vector divided by a vector. It doesn't make sense. Okay, so we do not have that. We only have vector multiplication. So in maths, it's like there's some rules or languages that, I mean, there's a grammatical rule for some certain languages. So English, they have a different grammatical rule with Spanish or some with Chinese. So there are different grammatical rules. So for maths itself, for different topics, they have their own set of languages. So for most of the time that you have deal with the real number. So basically, it's just a scalar. So a real number, so we can do division, multiplication, addition, subtraction, and so on, right? So for that is under that branch of maths, that branch of mathematics is called the number theory. And then we have this vector here. So for vector, we have a different set of rules. As I said, you can take it as a grammatical rule. So there's no division. So for vectors, we have addition, we have subtraction, and we have multiplication. Okay, so when two vectors in parallel, so x cap dot x cap is equals to y cap dot y cap. So if you refer to um, the xyz Cartesian, okay, so x cap and x cap, that means when we dot back, when we perform the dot product of the same component, of the x component or y component, so it's equals to 1. So if you look at this, if I draw something here, so I have a vector A, for example, and I have a vector B, theta, which is the angle made between vector A and B. So the definition of it, of vector, the dot product is A dot B equals to AB, magnitude of A, magnitude of A, magnitude of B, cos theta. So if I divide this, if I divide this vector B with the magnitude B, I have B cap, right? Let's say in the B direction. So what does it mean is, if we look at the expression here, if you look at the expression here, this basically signify is a projection of this vector, the projection of this vector onto B. The projection of this vector, so that the statement here is the projection of vector A onto B, right? So if you look at this triangle here, A cos theta is this length here, right? Is this length here. A cos theta is this length here. So it's a projection of vector A onto B. Okay. So is a great importance that if we understand the physical meaning to this. So so later on we will see some important application of this dot product. So if we have two vector signified by the Cartesian coordinates, okay, then these two, when we dot product, so it's simply the x component multiplied with the x component, y component multiplied with y component, and z component multiplied with z component. So one simple example here, find the dot product between vector A and B, then calculate the smallest angle between the two vectors. So we have vector A and B given. So the dot product, as I said, x component multiplied with x component, y multiplied with y, z multiplied with z, and the result give us 12. And applying the formula, the well-known formula for dot product, so we can find what is the angle made between two vectors. Okay, so the magnitude of A here is what? So we can calculate this. Magnitude of A is square root of 1 squared plus 3 squared plus 2 squared. So this is 14, right? And magnitude of B is square root of 2 square plus 4 square plus 1 square. So this is square root of 16, 17, 21. Yeah. So 12 is equals to square root of 14, square root of 21, cos theta. Yeah. So you can use your calculator to confirm this. So you should give you 45. Okay. Then we come to the cross product. So we normally associate cross product with right hand rule. So if you use your right hand rule now, that means you should use your right hand. Your thumb is the vector, the product vector, the vector product, the cross product, and then your finger, all your four fingers. If you can represent this, I mean, if you try to A cross B, that means if you try to imagine A move towards B, so your vector produced here is the unit vector. Sorry, the normal vector, the normal vector that is perpendicular to A and B, or perpendicular to the plane consists of A and B. So as I said, um, now you can use your right hand rule. Your thumb corresponds to the perpendicular vector produced by the cross product between A and B. So that means your finger, as I said, is moving from A to B direction. So this is the direction, estimated direction between the cross product between A and B. So the formula here is just A cross B, which is equals to AB sine theta in the normal direction. So this is the normal direction, which is perpendicular to the plane, that consists vector A and B. All right. So from the definition, the base vector of the Cartesian coordinate system obey the following right-hand cyclic relation. So so I can show you here what is this means. So let's say I draw the 3-dimension. So these are all perpendicular. The line are all perpendicular to each other. So assuming, I mean, my drawing does not show that, but assume that these 3 lines are all perpendicular to each other. That means X and Z are perpendicular. Z and Y is perpendicular. And same goes for X and Y is also perpendicular. So they are orthogonal with each other. So another word called perpendicular is orthogonal. And we have X cross Y. So again, if you are going to use right hand rule, X crosses Y. So the vector produced, the unit vector produced is in the Z direction. Okay. And we have Y crosses Z. Y cross Z. So if you look at the arrow that I draw, that means this is the direction of your finger curling, or the direction of your finger curl. So it is pointing in the X direction. And lastly, if we X crosses Z, sorry, Z crosses X. So in this direction, so the vector produced is in Y direction. Okay. Okay, so we use determinant. Okay, A cross B. So I know you should supposed to know this already. So so how we perform the cross product. So we use the determinant method to find what is the vector cross product. So if we cross the same vector, then it's going to be 0. So this can be easily seen as if two vectors are perpendicular, so the theta here is 0. So sine 0 is equals to 0. So same goes for if we're going to do a dot product between perpendicular vectors. So if two vectors are perpendicular, okay, if two vectors are perpendicular, for example, A and B are, so A dot B is going to be 0 without doing any further calculation, because I knew that. So based on the vector dot product, we knew that this is A, magnitude of A multiply magnitude of B, cos theta. So this theta, this angle here is the angle made between vector A and vector B. So in that sense, if this is perpendicular, so if I substitute 90 degrees here, so on my right hand side is going to be 0. So without calculation, so I know it's going to be 0. Yeah. So perpendicular vectors dot product produces 0. Parallel vectors when we try to perform cross product is going to be 0. So we have cross product, for example. So we have two vectors A and B given. So using the determinant method. So how is this obtained? So for the x component, how are we going to obtain x component? So first we cover this. First we are going to cover this and cover this. So 3 multiply -1 is -3 minus. So this multiply this. 3 multiply this term multiply -1. 3 multiply -1 minus 4 multiply -1. So 3 multiply -1 minus 4 times -1. So it is -3 plus 4. Okay. So same goes for y. So let's say I want to determine what is the y component. Same goes for this. Same thing, but remember the sign for y is negative. Yeah, the sign for y is negative. So the same, it is 2, 4, -1, -1. So 2 multiply -1 minus 4 multiply -1. So it's -2 plus 4. Yeah, so it's -2 plus 4. And then same goes for z. So z now the sign changes again, which is positive. So this is the rule that you should have already know. You should have already know. All right. So let's try some exercises, simple exercises. Example 2. You are given 2 points. This should be quick. 5 minutes. Okay, 5 minutes for A, B, C, D. Please try it. So I come back to you with my working step, the solution. The discussion later on. So in 5 minutes time, try to solve A, B, C, D. Sorry guys, please excuse me for a while. I come back to you in 1 minute time. All right. Okay. So the solution for this example, the position vector p. So this is the given coordinates. So we can write it as 0 to 4. So this is a normal representation for position vector of p. Okay. So we can write as 2y cap plus 4z cap, or we can write in the transpose form, the transpose form of coordinates as 0 to 4. So this is a transpose form. So the distance vector for p and q. So simply just find the vector pq. So for b, so this is OQ minus OP. So negative 315 024. So it's negative 3, negative 1, 1. Okay. And C is the distance between P and Q. So the magnitude of PQ. Simply just take the square root of each component square. So square root of so 11, right? And D, the vector parallel to PQ with magnitude of 10. So let's say let vector R be the vector parallel to PQ. So first I need to find the unit vector pointing in the direction of PQ. So the unit vector pointing in the direction of PQ. So it's simply vector PQ divided by the square root of 11. Okay. And therefore R, vector R is just 10 multiply PQ. Okay. So for everyone, okay? All right. So x, y, z is the same as I, j, k. Yes, Edin. Yes, correct. So I mean, maybe you have encountered I, j, k before, but they are different. I mean, they are different representation. So the representation of I is representing the direction of x, j represent the direction of y, and k represent the direction of z. So it's just different symbols being used to represent xyz direction. Okay. So moving on to next example. So you are given vectors a and b. Find the angle between a and b. All right. Again, this should be quick. Um, try this in 5 minutes time. So, all right, again, if you're wondering what is ax, ay, az, so basically they are just representation of in the x direction, in the unit vector x direction, unit vector y direction, unit vector z direction. So as I mentioned, they are just different representation. So I will try to use the um, I mean in later on, um, in the example later on, I mean in a lecture. So I will try to use my solution will be always based on x cap, y cap, and z cap. Okay. Okay, the solution for this example. First, we need to find what is the magnitude of A. And the magnitude of B. So we will apply the dot product to find the angle between these two vectors. So theta represent the angle made between the two vectors. Okay. All right. So that's all for, I mean, the brief revision for vector algebra. And now comes to the part on coordinate system and transformation. So we are going to apply the knowledge of the vector product, especially the vector dot product. And also we will go through briefly the differential element that is associated with the three orthogonal system that uh, that is going to be used quite often in this course. So I believe that you have came across the Cartesian coordinates. So when I say Cartesian coordinates, it means that it refers to the x, y, z. And the other two coordinate system, which is also called the orthogonal coordinate system. They are cylindrical coordinate system and also spherical coordinate system. So when I say orthogonal, so this word here, orthogonal, so it means that the axis that corresponds to these coordinate systems for cylindrical coordinate system and spherical coordinate system, the axis is always in it is 90 degrees to each other. So we'll see that briefly now. So for rectangular, we already know that x, y, z are perpendicular to each other, so therefore they are called orthogonal coordinate system. So I don't have to go through the how you locate these points here. So I believe you should know how to locate these points in 3 dimension for Cartesian coordinate system or rectangular coordinate system. So the range of this XYZ, so they extends to infinity. So the range can be any value. X can be any real value. So I'm talking about real value, yeah. So it can be any real value. So this infinity just represent a very large number. It can be any value. So a vector A in Cartesian or rectangular coordinates can be represented by the component of x. So the index here, x, small x, represent the x component, and y component and z component. And normally I will just write it as ax, x cap, plus ay, y cap, plus az, z cap. So this is the normal notation. I would call this my notation. This is the normal notation that I will always use when I write down my solution or my explanation to you. So I will always use this notation. Okay. So first we come to how the differential length or displacement is being defined here. So imagine, so I'm going to redraw this cube here, this this rectangular cube. So I'm going to draw back this cube here. Okay. So imagine that you start at this point. Okay, this vertices, this edge here, this vertices here. So this is your point here. And imagine now you represent this point. You represent this point, and you're going to walk a small displacement towards the x direction, the x. Okay, and then sorry, this is not the x. So here is the x. Sorry. So let's say we are going to. So let me restart this discussion. So let's say we start from here. Maybe I use a different color. So this is the initial point that you stand. Okay, this is the initial point that you stand. This red dot here represent you. So assuming that now you try to move a small distance from this point to here. So you landed in this point now. This is the point, and this length here is dx because you are moving in the x direction. So there are small changes. So this is a small length. So normally we represent this small distance here as dx. And then now from this point, you move across to the y direction and you landed here. So you landed here. So again, this motion here, I mean, this displacement here is a small length, small displacement length in the direction of y. Okay. So I should put direction x, y cap and x cap here. And finally, you move across to this point. So you are landed now at this black dot here. Okay. So this length here now is your, so this length here, the displacement length is dz in the direction of z cap, in the direction of z cap. So starting from here, so your initial point to here now, so maybe I use a different color, sorry. So your initial point to here now, so you can imagine that arrow now. So I hope it is three-dimensional enough for you to visualize. So from this point, from this red dot to the black dot here is the differential length dl. Okay, it's a differential length dl. So normally it is written as this differential displacement, or we call displacement. We write as dl, okay, dx x cap, okay. So and dy y cap plus dz z cap. Okay. So same as how we find the position vector, the position vector of between 2 points. Okay, between 2 points. Okay, so now what about differential volume? So when we talk about volume, so we need to find the area, and we then multiply the height, then we get the volume. So the differential volume, so due to this displacement, so when we trace this, so as you can see, this is a small cube. So the differential volume is simply dx multiply dy multiply dz. Okay, so when we talk about volume, there is no direction. Okay, there is no direction. So as you can see, when we say displacement, there is a direction. So we have to associate the displacement or differential length with the direction of x, y, z. Okay. However, for differential area, this is important. So for differential area, we associate, so we have, if we look at this cube here, if we look at this cube here, so we have 6 faces, right? So top and bottom, two area, front and back, two area, front and back, two area. The side of these two is altogether 6 area that make up of this cube. So when we refer to a certain differential area, so for example, when we refer to a certain differential area, we always associate that area. Let's say, for example, maybe I will erase this for now. So let's say I shaded this area here. So this area here is dx multiply dz, right? So the area of the shaded red area, so we can write it as dz dz multiply dx. Yeah. So and the area normally we associate with the normal direction pointing out, pointing perpendicular to this area. So by imagining, if this is the shaded area, the direction, the normal direction perpendicular to the area is in the y direction, right? So the differential area for this is in the y direction. Do you get what I'm saying? This is important for you. So this is where we always um, I mean, this is important because we are going to apply this simple understanding when we deal with the calculation of the electric field or magnetic field. So do you understand what I have explained so far? I mean, for differential area, so earlier I mentioned that volume, there is no direction for volume. So of course, area also suppose the area, we do not associate area with direction, but in this course, we need to associate them with the direction of the area. So the direction of the area is referring to the perpendicular vector that is pointing, the direction is perpendicular to the surface of the area. So by looking at the shaded area, the red shaded area, if you imagine, then the direction perpendicular to this area represent the differential area. So it is in the y direction. It is in the y direction. So do you get my explanation? Okay. So, oops, sorry. And then we have also, if you look at dx multiply, sorry, if you look at dx multiply dy, so this represent this area here. This represent this area. And for this area, the vector perpendicular to this surface area, is in the z direction. And lastly, this surface, it is a bit convoluted, but for this surface here, maybe I draw it. Maybe I draw it for this surface. So for this surface here, it is dy. It is actually dy multiply with dz. Okay, and the vector direction, which is perpendicular to this surface, is in the x direction. Okay, so remember, for this particular uh, application, it is a normal. It is conventionally done for this course, that we associate the differential area, as I have just explained just now, with the vector direction that is perpendicular to the surface, with respect to the surface. So we'll see a few more example later on, that for other orthogonal system. So now come to cylindrical coordinates. So normally, for cylindrical coordinates, we have rho, phi, and z, and sometimes it is represented by small r, phi, and z. Okay. So some I mean some of you may ask, how do we differentiate between cylindrical coordinates and spherical? So spherical, we also have a radius. So for spherical, we always use capital R. We always use capital R, theta, and phi. Okay. So can I use small r? Yes, you can use small r as well. So the representation, can I use rho? Yes, you can use rho as well. So as the variable that you can apply to is that to distinguish between cylindrical and spherical coordinates. How do we distinguish? Is that you must be you must be um, you must understand that for spherical there are two there are two coordinates which is in angle, in degree or radian. So this is angle, this is angle. So it is in degree or radian. Okay. Whereas for uh, Cartesian XYZ, we do not have everything. It is in unit metric, right? Like meter, centimeter. So whatever uh, there is that whatever unit that is associated with distance. While cylindrical, we have we have associate r with length, the radius with length, z also is length, while phi is angle. So that's how we distinguish between cylindrical and spherical. So what I'm trying to tell you here is don't get confused. I mean, sometimes it's confused. It is complicated, but because of different symbol being used or different variable being used, but you have to keep in mind that if you are aware, if you well know, if you know well the, say, for cylindrical or spherical coordinate system, the implementation of this variable here should be not a problem. Yeah, shouldn't be a problem. Okay. All right. So again, this axis, the cylindrical axis, are always perpendicular to each other. So as the name implies, this axis here should trace a cylinder, should give you a cylinder shape. So first we start with the range of the variable. So rho represent the radius. So it can range from 0. That means you start from here. So let's say this is the reference point. So it starts from here to any value, to infinity, yeah, to any value, to any real value. While phi, starting from the x-axis and the direction of positive value phi, it is counterclockwise. Yeah. So if you look from here, the direction of phi is counterclockwise. Okay. So it is 0 to 2 pi. That means 0 to 360 degrees. Okay. If you look from the top. And again, z, the z value, which is part of the cylindrical coordinate system. The range of z value can be from any value, in large value to negative infinity to positive infinity. Okay. So now, since we knew that rho is radius, so the direction should be radially outwards. And phi is the rotation of if we take any points, let's say I have, let's say, two 90 degrees tree, for example. So how we trace it is radius 2, for example. Radius 2 is here, for example. 90 degrees. So 90 degrees is from here to here, right? and then 3. So this is the point. So this, let's say this point is 2, 90 degrees, 3 unit. So 2 unit radius, 90 degrees, referring to this, referring to the constant plane of phi at 90 degrees, and then 3 is the unit for the z-axis. Okay. So say that this is the point, yeah. And for the unit vector, so one is pointing radially outwards. So this is a unit vector pointing radially outwards. And the z is perpendicular to the radial, the radial unit vector for rho. And the phi is also perpendicular to both z and rho. So even though you say that, okay, because we are looking at this point here, so why is it that you may ask, why is it that is perpendicular? It is because even though this is a curve, because we are taking at a point, so we are looking at a point. So imagine that if, let's say, we are trying to move this point here. So if you can see my sketch, so maybe I use a different color. So if this is the point that we are looking at, and move to is moving, so this is the direction here. So it is perpendicular to the curve, right? Which is the, I mean that, imagine that you are moving constantly, okay? I mean with a speed, but the velocity will be different, right? So the angular velocity will be different, right? Even though you are moving at constant speed, but the angular velocity will be different. So imagine that this is your position. The red, I mean the one that I pointed here is red. The red dot, so when it moves, so this is going to be a perpendicular direction. So therefore, these unit vectors here, it is said to be orthogonal. So since we already knew that rho and z, it is perpendicular, and therefore the phi direction is also perpendicular to both. The phi is perpendicular to both rho and z. So same case if we perform the dot product for the radial and phi and z. So the unit vector for rho, phi, and z, when we perform the dot product, is always equals to 1, while the the perpendicular vector rho between rho and phi, when we perform the dot product, is going to result as 0. And it is cyclic. So for example, same goes for how we determine the product of cross product between two vectors. So bear in mind all these are perpendicular. Okay. So if rho crosses phi, so it is in the z direction. Okay. While phi crosses z, it produces in this direction. So I have indicate the crossing, I mean using the right hand rule. Okay, I have indicate the with color of the cross product. And lastly is z crosses rho. So z crosses rho is here. Will produce phi. Okay. And what is the relation between Cartesian and cylindrical coordinates? So if let's say from here to this point is your length is your radial length, and it makes an angle phi between x, right? Between x. So using our triangle, I mean we apply sine and cos to find what is the decomposition length, and also for x and y. So we can associate this as x is equals to rho cos phi, and also y equals to rho sine phi. So this should be, I mean, this should be easily understood for you. Should be easily understand for you. So we are just applying the triangle solution, given that the hypotenuse length, which is rho, and then we can decompose the adjacent length and also the opposite of the adjacent, okay, of the triangle. So basically, rho is, if let's say at this point here, the Cartesian is defined as xyz for Cartesian, and for cylindrical is defined as rho, phi, and z. So the relation can be easily seen that rho is square root of x squared plus y squared, and phi is basically arctangent y divided by x, z is equals to z. Okay, so this is how the relation between rho and rho phi z with xyz. In the other hand, on how we convert rho to x, we can use, as I said, the decomposition of the length of the triangle. So this can be easily see that if this is the given length rho, and if you want to find the x length, so basically we are projecting rho onto x-axis. Similarly, we are projecting, let's say we want to find y, we are projecting this length here to y-axis. So the differential length, the differential length, and surface and volume, following my earlier explanation. So it's the same. It's the same concept. So let me try to draw this again, for this small cube here. So so assuming that, let's say you are here, you started at this point. So you want to reach this point here. So you want to reach this point. Okay. So we start to walk in this direction. So now we are dealing with cylindrical coordinates. So from this point to this point, the displacement is d phi. Yeah, the displacement is d phi. Okay. And after that, you move across this. So if this is a small angle, I mean this is for cylinder. So we are moving to a small differential arc length, and therefore this is associated with the angle d phi. So from here to here now. So this is rho d phi. Okay. And now you are at this point. To move to the green point, it will be dz. So associate with the direction. So we have rho cap, and then we have phi cap here, and z cap. Okay. So this is the differential displacement, dl, from here to here. So dl. So we add all this displacement. The displacement due to the radial direction, the phi direction, and also the z direction. And also the surfaces, as I said, as I mentioned just now, the surfaces is, so for example, so I will just take one example and the rest is the same. And how we interpret this. So let's say I'm going to take this surface area. So so let's say this is the surface area. Okay. So this red, I mean the shaded area that I pointed out here is referring to rho d phi. So this is the length, one of the length of the surface. Rho d phi multiply with dz, right? Multiply with dz. So the differential area for this surface is rho d phi multiply with dz. And as I have mentioned just now, so we associate the differential surface with the direction. So how we identify the direction? So the direction that is perpendicular to the surface. So the vector which is perpendicular to the surface is phi cap. Yeah, the unit vector phi cap. Okay. And the volume is just the differential volume is then dv. It's just rho d phi d rho, sorry, rho d rho d phi dz. You know, I don't know why is it looks like that. D phi, why is it like that? I think there's some lag. Sorry, just so the differential volume is then rho v. Dv is rho d phi. Sorry, rho d rho d phi dz. Okay. So there's no direction associated with the volume. Okay. We have entered the lecture session now, but I have continued for more than 1.5 hours. So maybe we should take a break. But before we take a break, I want to ask one. I want to have a quick check with you. So far, I know that you have go through this course before. I mean the mathematics course, but so far it is still. I mean you understand, right? All this explanation that I have mentioned just now. All right. Okay, Cockwing. Yeah, I will use the laser pointer. The last part need to digest a bit. Okay. All right. So we will take a short break now. We'll take a short break now. About 5 to 10 minutes. So I'll talk to you again in 10 minutes time. All right. So you can take a toilet break and then come back.